Good morning, my dear students. Welcome for the second session lecture on interference of light. So in the last class, we have discussed about the theory of biprism experiment, and also we have discussed how to determine the wavelength of light in a biprism experiment. And today, let us discuss about how the fringes gets displaced when a thin film of a denser medium is interposed in one of the interfering beams, that is displacement of fringes by the introduction of a thin film. Look at this diagram first. S1, S2 are coherent virtual sources. S is a virginal source or virginal slit. D is the distance of separation between S1 and S2, and capital D is the distance of the screen from the plane of the two slits. That is in Young's double slit experiment. If it is biprism experiment, so it is capital D is A plus B. So distance between the slit S and the eyepiece, that is capital D. Now light from S1 will reach point P traveling through distance S1P, and similarly light from S2 will travel S2P in reaching point X, and say X is the distance of some arbitrary point P from the midpoint O on the screen. So before introducing this thin film of a denser medium, at point O you will have a central bright fringe. If you introduce this thin film of thickness T and refractive index N in one of the interfering beams, it may be S1P or S2P, then we observe that the central bright fringe will be shifted through some distance, which can be calculated using this formula. S is equal to N minus 1 into T divided by lambda. We are going to deduce this expression for the displacement of the fringes by the introduction of a thin film, and the number of fringes through which the central bright fringe gets displaced. It is S, it is N minus 1 into T by lambda. We are going to derive even this formula. Now, let us come to the explanation part after observing the figure, because I will move the screen. So, thin film refers to any denser medium whose thickness is of the order of wavelength lambda. For example, mica sheet, or it may be ceramic or thin glass plate, etc. So in the figure, S1, S2 be the two virtual coherent sources separated by a distance D. Let O be the midpoint of the screen. Equidistant from S1 and S2. Let the distance between the two coherent sources and the screen be capital D. When a thin glass plate, capital G, of thickness T and refractive index N is placed in the path of the light from one of the two sources as shown in the previous figure, the central bright fringe is shifted to the point P due to the change in the path difference. The light from S1 reaches point P has to travel a distance S1P minus T in air and distance T in glass plate, that is thin film. If C and V be the velocities of light in air and in the glass plate respectively, then the time taken by the light to travel from S1 to point P is given by, let us call the time as T1. So distance traveled in air is S1P minus T, that divide by speed of light in air, C. The first term gives you the time taken by the light to travel in air from S1 to point P, plus T by V gives you the time taken by the light to travel inside the thin film of glass plate. So therefore the total time to travel for light to travel from S1 to point P in the above figure is given by equation 1. Similarly, the time taken by the light to travel the path S to P is T2 is S to P divided by C. Since the time taken by the light for both the paths is the same, because before introducing the thin glass plate, S1O will be equal to S2O. It means both the light waves coming from S1 and S2 in reaching the midpoint at point O will be the same. Now the introduction of thin glass plate has shifted the fringe from O to point P. Therefore, the time taken to reach point P by the two light waves must be the same. So therefore, equate from equations 1 and 2, T1 equals T2. This is T1, S1P minus T divided by C plus T by V, which is equal to S2P by C. Since N, refractive index is C by V, which implies that V is equal to C by N. Just cross multiply, we'll get this. So on substituting, we get S1P minus T divided by C plus T into N divided by C equals S2P divided by C. So denominator is C. So multiply throughout by C, you will get S1P minus T plus T into N is equal to S2P. Therefore, S2P minus S1P is equal to N minus 1 into T. This is the extra path traveled by the light waves when the thin glass plate is introduced in the path of one of the interfering waves. Therefore, the path difference between S2P and S1P is S2P minus S1P plus N minus 1 into T. So therefore, S2P minus S1P minus N minus 1 into T. So from Young's double slit experiment, the relation for path difference is given by S2P minus S1P is X into D by small d. Now substitute this. Therefore, the net path difference is XD by capital D minus N minus 1 into T. For constructive interference, path difference should be integral multiples of wavelength lambda, that is m lambda, where m is 0, 1, 2, 3 is a positive integer. Therefore, for constructive interference, xd by capital D minus n minus 1 into t is equal to m lambda, where m is an integer. So equation 6 holds good for constructive interference. So the position of central bright fringe when the glass plate is introduced in the path S1P is obtained by putting m is equal to 0. So if you put m is equal to 0 in the above expression, you will get position of central bright fringe. So if you put m is equal to 0, you will get this equation. In place of x, you write x naught d by capital D minus n minus 1 into t is equal to 0. Next, x naught will be capital D by small d into n minus 1. Equation 7. If n is greater than 1, x naught is positive. This shows that the central bright fringe will move upwards when a thin glass plate is introduced in the path S1P. Similarly, if the glass plate is introduced in the path of the second beam, the shift will be downward. So therefore, the shift of the central bright fringe from the midpoint O on the screen is given by equation 7. X naught is equal to d by small d into n minus 1. Similarly, for the first bright fringe, m is equal to 1, the position x1 of the first bright fringe can be found using this formula. X1 is equal to d by d into lambda plus n minus 1 into t. So therefore, fringe width beta is x1 minus x0. Substitute from the above two equations, 7 and also this equation. You will get beta is equal to lambda d by small d, that is equation 8. So the conclusion is introduction of glass plate, that is thin film, will not change the fringe width beta, but the fringes gets shifted. The whole fringe pattern gets shifted by an amount x0. So therefore, from the above equation 8, we can write beta by lambda is equal to d by d. Substituting in equation 7, shift in the fringes, x0 will be beta by lambda. Instead of d by d, I am writing beta by lambda into n minus 1 into t. If the number of fringes displaced from the center on the introduction of the glass plate is m, then the total fringe width, the total shift will be x naught will be m into beta. So in place of x naught, you write m beta. So m beta is equal to beta by lambda into n minus 1. Cancel beta beta on either sides. Then we get m is equal to n minus 1 into t by lambda. That is equation 11. Thickness of the glass plate T is equal to m lambda divided by n minus 1. That is equation 10. So equation 10 gives you thickness of the film, which can be calculated by this experiment, and equation 11 gives you the number of fringes shifted, can be calculated using equation 11, and the distance through which the central bright fringe gets shifted is calculated using equation 12. So all the three equations 10, 11, 12 are important. So this derivation may be asked. So the conclusion is, when a thin film like glass plate or mica is introduced in the path of the one of the interfering beams, the whole interference pattern gets shifted through some distance x naught given by equation 12, and the number of fringes gets shifted is given by equation 11, and you can find what is the thickness of such a thin film using equation 10. Next, let us discuss about what is a Stokes treatment of reflected and transmitted amplitudes, how the phase change occurs on reflection at a denser surface or at a rarer surface. Now look at the two figures. I will not go in detail because the application of this will be used in the next derivation. Therefore, you remember what happens to the phase when reflection occurs at a denser surface. So in the figure, AB represents the surface of a denser medium. So below AB, you have a denser medium, that is figure 1. And above AB, you have a rarer medium. For example, rarer medium may be air and denser medium may be glass or water. So in the first figure, PO is an incident ray, I is the angle of incidence, N dash is a normal drawn to the surface AB at the point of incidence, that is point O. So angle between the incident ray and the normal is represented as I, which is angle of incidence. And the reflected part of the ray is OQ. OQ is reflected ray. And OR is the transmitted or refracted ray. And R, small r, denotes angle of refraction. Let A be the amplitude of light of the incident ray. A part of it gets reflected. So therefore AR is a reflected part and AT is a transmitted part. Similarly, if you reverse, suppose the ray is incident along RO as shown in the second figure, AT is a amplitude of the incident ray. It undergoes reflection in the denser medium, AT into R dash, AT into R dash. R dash is reflection coefficient for the denser medium, and the transmitted light is AT into T dash along OP, AT into T dash, And similarly, if the ray is incident along QO, if AR is reversed, all are reversed in this figure. AT and AR are reversed. So AT will undergo reflection. The reflected part in the denser medium is AT into R dash, where R dash is the reflection coefficient in the denser medium. And transmitted into the rarer medium is AT into T dash. T dash is the transmission coefficient from denser to rarer medium. Similarly, if you reverse AR along QO, it will undergo reflection. AR into R, that is AR square, is a reflected part in the rarer medium, and the transmitted part is AR into T, ATR. So from these two figures, now we can understand what is Stokes treatment. The reflected waves are accelerated by half a wavelength and their phase is increased by pi or part difference by lambda 2 on reflection from the mirror. That means when reflection occurs at a denser surface, there will be change in path equal to lambda by 2 or the phase changes by pi radians. Let us look at the mathematical part. In figure A denotes amplitude of the incident plane wavefront PO. AR, amplitude of the reflected wave OQ. AT, amplitude of the transmitted wave OR. In figure B, AR, incident amplitude. AR square, reflected amplitude. ATR, transmitted amplitude after reversing the path of light. Similarly, if the refracted wave is reversed, reflected amplitude is ATR dash, transmitted amplitude is AT into T dash along OP. Hence, by the principle of reversibility of light, this you can understand from the above figure, AR square plus AT into T dash must be equal to A. Look at the figure, figure A. A should be same as AR square plus AT into T dash. This is after reversing the path. AR square plus AT into T dash must be equal to A. So cancel A. R square plus TT dash is equal to 1. Therefore, T into T dash is equal to 1 minus R square. That is equation 3. And for transmitted part, ART plus ATR dash must be equal to 0. Go back to the figure. Here, ATR plus ATR dash must be equal to 0 because here there is no reflected wave in the second medium. This sum must be equal to 0. So therefore, from second equation, ART plus ATR dash, cancel AT, you will get R plus R dash is equal to 0. That is R is equal to minus R dash. That is equation 4. Which implies that phase change is pi radians, which is equal to lambda by 2. This is a Stokes treatment. Just remember, when reflection occurs at a denser surface, that means light should be traveling from denser to rarer. When reflection occurs, there is phase change of pi radians or path difference equal to lambda by 2. That means if a crust is falling on the surface of the denser medium, after reflection, a trough will be created or vice versa. There's a meaning from Stokes treatment. Let me stop at this stage. The next derivation, I will take it up in the next class.